Hello. I'm trying to make my own digital decoders from scratch for my model trains, both for fun and with the aim of saving a lot of money. 8 or 9 months ago I made a gentle start by programming a Raspberry Pi Pico microcontroller to capture some DCC instructions from the tracks, and made a video about it. Since then I've moved on to programming a smaller ATtiny85 microcontroller which can operate some LEDs in response to certain DCC commands. If the workings of the DCC signal and instructions are a mystery to you, then it might be worth watching the other video first, then coming back to this one. It's video number 47. I've put a link in the description. I hadn't programmed an ATtiny85 before, and the first step, as seems standard for microcontroller programming, is to get an LED blinking. But getting just to that point took me lots of attempts over quite a few weeks. I used a genuine Arduino Nano Every as the programmer through Arduino IDE, using a whole range of tutorials for guidance. At first I used this clip to get connections to the ATtiny's pins, but it didn't seem to clamp on properly and didn't work, so I got this other kind. That didn't seem to work either, and so I got some SOIC to DIP boards and soldered the Tiny to one of those. But I still couldn't get code to upload. It always failed with some kind of error. As a last-ditch attempt I bought some DIP packaged ATtiny85s and one of those worked. So either my original SOIC ATtiny was broken on arrival, or I broke it during soldering. I then soldered up another of the SOIC kind, but more delicately, and I've been able to successfully program that one lots of times. I'm not trying to make another ATtiny85 programming tutorial here. Lots exist already, so I'm glossing over this process, but I've added some notes to the description to detail what worked for me, in case you're in the same situation and in case it helps. As with other microcontrollers, the ATtiny85 supports external interrupts. If the voltage changes on the interrupt pin, then that triggers a particular function, the interrupt service routine, to run pretty much immediately. These are what I wanted to use to react to the voltage changes that form the DCC signal. I eventually got an experimental version of interrupt handling working, where an interrupt toggles an LED. It took a lot of searching to arrive at what was necessary. I'm not sure how all of these things work, but I think the boards manager I installed in Arduino IDE provides its own implementation of the Arduino library of functions that's made to work on the various ATtiny microcontrollers. In the Arduino library there's an easy-to-use method for setting up interrupts, but it doesn't seem to work on the ATtiny85. I eventually found a forum post somewhere where this was discussed, and it included a code example for setting up interrupts another way, and that way has worked for me. The next challenge was working out what I could do, related to DCC, that would be minimal and which I'd be able to measure in some way. Unlike a development board, such as the Raspberry Pi Pico, I wouldn't be able to get a readout on my computer about what was happening. I think with some extra software on the Tiny it's possible to set up a connection over USB, but I haven't had a go at that yet. On my computer I wrote code in C that mimics the functions I'd need to use on the Tiny, and wrote some DCC signal handling to detect a baseline DCC packet for speed and direction. Using this approach, I could precisely simulate the ones and zeros of a DCC signal, which enabled me to develop the code and work through errors in an environment where I can easily have feedback about what the code is actually doing when running. I found this part very straightforward and enjoyable. It's been about 20 years since I did much programming in C, but I'm used to programming in this kind of environment in other languages like Java and Python. I'm far less competent with electronics. Essentially, everything I've learned is from what I've gradually done on this model railway over the last few years. Last time, with the Raspberry Pi, I used a voltage regulator to reduce the voltage of the DCC signal input to the microcontroller. One theme in comments on that video was to tell me that using a voltage regulator on a high-speed signal is a terrible idea, and that better approaches would be to use resistors to make a voltage divider, or to use an optocoupler. My Raspberry Pi was powered from my laptop, but ultimately a locomotive decoder needs to be powered from the DCC track power, and for this I'm sure a voltage regulator is ideal. My DCC system produces 13 volts at the track, which flips direction to form the DCC signal, so I used Schottky diodes to rectify the alternating current into the voltage regulator, which brought the voltage down to 3.3 volts to power the ATtiny. This didn't work as I'd expected though. I had some kind of LED blinking code on the ATtiny, but it wasn't producing the pattern I'd expected. After various experiments with the LED code, it seemed like maybe the Tiny was restarting a lot, so I wondered if it was losing power when the track voltage flipped. In an ideal world, there wouldn't be any drop in power on a DCC system, but the reality is that it takes a tiny bit of time for the electronics to flip the phase of the voltage. The NMRA electrical standard specifies how long is acceptable, and in that time the overall voltage can drop. That being the case, I wondered if using a capacitor as a stay-alive might work, and I already had this tub of assorted capacitors because lots of electrical circuits seem to need them. I don't know much about using a capacitor, but from what I found I know it mustn't be connected to a higher voltage than its specification. Mine are well above the 3.3 volts coming from the voltage regulator, so that bit is fine, but I don't know what the capacitor's output voltage would be. But the ATtiny is cheap enough, about £2, and I had something like 5 available, so I just tried a capacitor anyway, connecting it in parallel with the ATtiny. I also changed the LED code to just have the LED on continuously, and with the capacitor in place that started working. I think I tried this with a 10 microfarad capacitor and then with a 47 microfarad one, and each one worked. As a side note, several commenters on my other video were really surprised I was able to record meaningful DCC signals via this regulator, pointing out that the job of a regulator is to stabilize the voltage level rather than track it. But I think this experience with the ATtiny demonstrates the voltage regulator stops outputting power extremely quickly after it loses it from its input. Maybe it starts again equally quickly. With a Tiny that was now able to stay on, I turned my attention to processing the DCC signal. I've had this pack of assorted resistors for several years, so having done some internet searching about voltage divider circuits, I was able to make one of those. I used an online calculator to get the right ratio, using 1 kΩ and 3.3 kΩ resistors to drop the 13 volts to something near 3 volts. Whilst it's the resistor ratios that determine the voltage, I figured that since V equals IR, the higher the resistor value, the lower the current that's going to end up in the circuit. I think about 3 milliamps in this case. The arrangement looked something like this. I didn't take any photos of it originally. This is a reconstruction. The diodes are so that it only allows current to flow when one rail in particular is at the high voltage. I've since realized there was at least one major flaw with this. The voltage coming through the divider would have been at the ATtiny's high level, but I didn't have anything to pull the interrupt pin to a low level when the DCC track voltage went low, which means the level at the pin would only ever have been high or floating. Floating means it would produce essentially random readings based on electrical noise from other things going on. I can't remember what I then tried to do with the DCC signal, but whatever it was, it didn't work as I expected at the time, and I do remember noticing the ATtiny was still restarting occasionally, even with the capacitor in place. After a fair bit more searching online, I discovered that voltage regulators usually need capacitors at their input and output in order to be stable. Looking at the datasheet for my regulators, it says they're stable even with a small capacitor, so that confirmed the need for at least one capacitor. By this point, the sprawl of crocodile clips and connectors had become difficult to manage, so I finally got more breadboards to make all those connections neater and easier to set up. I'd also bought a couple of voltage rectifiers at some point, so used one of those instead of the 4 separate diodes. Adding a capacitor in parallel to the voltage regulator's input sorted out its stability. Since then, I haven't had any problems with the ATtiny restarting. I still wasn't having success with getting the ATtiny to react to DCC instructions, and I was gradually cutting down the code I had running on it to get the LEDs to illuminate or blink in certain conditions. I began to think the voltage divider approach wasn't working, and since it leaves the Tiny vulnerable to surges in track voltage, I decided to switch to an optocoupler instead. I'd bought a pack of PC817C optocouplers to experiment with, and with one of those connected to the interrupt pin, I eventually started being able to get some kind of activity from the interrupt handler. I set this up in the same way as I found in some instructions in online articles. A high voltage at one of the tracks will be reduced by the resistor, then activate the LED inside the optocoupler, which will activate a transistor between the optocoupler's 3rd and 4th pins. With the ATtiny's interrupt and ground connected to those pins, an activated optocoupler causes the interrupt pin to be at a low voltage. When there's no transistor connection, the interrupt pin is only connected to the input voltage of the Tiny, going via this pull-up resistor, which sets the pin to a high voltage. A pull-up resistor is a normal resistor, just used to connect a pin to the high voltage of the system until something else connects the pin to the low or ground voltage of the system. It prevents the random floating pin values. To start with, I didn't include this extra diode because the optocoupler has one anyway, and I don't see why you'd want current to flow this way. After some searching, I found it's there to protect the optocouplers, because they can only tolerate a maximum reverse voltage of 6 volts. Without this diode, they were getting a reverse 13 volts from my DCC system. As far as I can see, allowing current to flow in this direction is just going to waste energy through the resistor, so I added the protection diode this way to block current flow. These diodes can tolerate a reverse voltage of up to 40 volts. The ATtiny has built-in pull-up resistors, which I activated on the interrupt pin, and so I didn't include the external pull-up connection in the optocoupler circuit. But I didn't get the expected results until I added that external connection. To start with, I was just setting the internal pull-up via the Arduino pin mode function, but since it didn't appear to be having any effect, I had to read through the bits of the ATtiny85 datasheet that mention pull-up resistors. I'm gradually getting better at being able to read through this sort of information. From what I've found, there's a bit that controls whether or not the ATtiny's pull-up resistors are all disabled. It defaults to 0, meaning they're not disabled. To be sure, I set this bit to 0 in my code too. After that, there's a register that determines if pins are for input or output, and another register that determines whether or not each pin's pull-up resistor is enabled. The interrupt pin I'm using is called int0, which is on port B's second pin, which is physical pin 7. I've been pretty confused by these pin number schemes, and so have plenty of other people new to this kind of thing. But the more time spent reading the datasheet, the clearer it becomes. I set the relevant pull-up resistor bit in the port B register, but even with that, it still behaved as though there was no pull-up resistor. Reading further through the datasheet, I found it's possible for the settings for pull-up resistors to be disabled by a signal. The datasheet says those signals are sent internally if certain features are enabled. In the case of port B pin 2, it looks like that's done by something called USI. The value referenced in this table only appears in this table, but elsewhere in the document there's reference to 2-wire USI and a register that controls it. The values default to 0, or off, but I explicitly set that register to all zeros just to be sure. That didn't make a difference. Out of curiosity, I asked Arduino IDE to show me the source for the pin mode function. When the pin is used as an input, a second register has a bit set to 1 for input pull-up, else set to 0. So I imagine that's the port B register. As a final experiment, I commented out all the bits I'd added about pull-up resistors and changed the pin mode to just input, and the Tiny behaved in exactly the same way at the track, needing an external pull-up resistor. I've resigned to using the external pull-up resistor for now. A 3.3 kΩ one seems to work. It's worth noting that the PC817 kind of optocouplers are considered to have a slow response time. The ones I got are from Amazon and don't have a datasheet, but looking at similar ones elsewhere, the response time is typically 3 or 4 microseconds. Given the shortest valid DCC period is 52 microseconds, these should be fast enough, so I intend to stick with them because they're cheaper and don't need as many pin connections. So by this point, after quite a lot of trial and error and learning, I had an ATtiny85 that would stay on and which was getting interrupt signals triggered by the DCC signal. But there was still a long way to go before having something that would respond to speed and direction commands in the way I expected. In the software, I've set the interrupt service routine to be triggered whenever the interrupt pin level changes. The first change is considered to be a rise in logic level, and the next one is considered to be a fall. The time between them determines whether the DCC bit value is 1 or 0. The routine then continually flips between rise and fall. It doesn't matter if the code is right about whether the level change was actually a rise or a fall, because the DCC signal is mirrored on the other rail. I wrote a few different overall approaches to processing the DCC signal, but they all use this method to detect 1s and 0s. The ATtiny is an 8-bit system, so I assume any numbers in the program which are longer will require more instructions to handle them, and so I've tried to minimize use of them. The Arduino library provides a micros function for tracking time at the microsecond level, but it returns a 32-bit number. That's a lot bigger than I need it to be, but to keep things simple for now I'm using it, and minimizing the number of places my code handles it. My first approach to processing the signal had a fair bit of logic in the interrupt service routine. It had a 16-bit buffer that kept track of the 16 most recent DCC bit values. It compared the bits buffer to a DCC preamble bit mask, and once a preamble had been detected, it would copy subsequent bits into DCC packet bytes, until detecting either the end of the packet or filling the bytes buffer. Once the end of a packet was detected, a separate function took over to analyze the DCC bytes. Until that function was complete, the interrupt service routine would exit without doing anything. Although the interrupt service routine was dealing with several Boolean flag checks and 16-bit number operations, I thought those operations should all be pretty efficient. This code didn't work. I gradually cut it back and added various LED flashes for feedback, but I think there must have been too much work in the interrupt service routine to reliably finish within the duration of a DCC 1-bit. It's worth noting that the micros function runs off a timer. I don't know exactly how it works, but it's there and regularly doing work with a 32-bit number, so it's not just my own code that needs to fit within the duration of the DCC bits. With a clock speed of 8 MHz, 416 instructions can happen during the minimum valid DCC duration of 52 microseconds. I've never written assembly code, but that seems fairly tight. I think just incrementing an 8-bit variable takes 3 instructions. My next approach was to have the interrupt service routine store 255 bits into a buffer, each DCC bit as an 8-bit integer, and then hand control over to a different function to make sense of the bits. The DCC packets I've read about so far are between 38 and 65 bits, when including the preamble, so it seems like there's a reasonable chance of capturing a whole packet. This approach is the one that has the smallest amount of work inside the interrupt service routine, and apart from the timing measurement, it deals only in 8-bit numbers. This actually caused a gotcha for me that took a while to narrow down. The logic here was sound. I wanted to keep storing bits in the buffer until the buffer was full. But with an 8-bit counter and a maximum buffer index of 255, this condition was never actually being met. After the counter got to its highest possible value of 255, it would be incremented, but that would make it a higher value than it could hold, so it would overflow and go back to 0, and then the whole process would continue forever. Reducing the buffer size by 1 was the best compromise to fix this, because it doesn't add any extra processing time, but makes little difference to the number of bits captured. All DCC packets that I've read about start with an address byte, so at its simplest my code was looking for the packet preamble and then giving feedback about the address byte by flashing a red LED to represent a 0 and a green LED to represent a 1. For a while I thought the address values were a bit random. It would sometimes output the number I expected based on the commands I entered on my DCC controller, and other times totally different numbers. One day, after watching it for a while, I realized it was outputting mostly the numbers of the different addresses for which I'd entered commands, but long after I'd entered those commands. The DCC communications standards say a command station should repeat commands as often as is practical. I'd assumed that just meant lots of repetitions straight after the command is first issued, but perhaps the system I've got repeats them every so often a long time afterwards. This would make sense because if a locomotive loses electrical contact with the rails and stops, that also means the decoder loses power and switches off. But you can give the loco a nudge to get it back in contact and then it carries on with what it was doing before. It's possible the decoders write their last instruction into permanent memory, but a repeated instruction on the tracks would allow them to carry on even if they don't remember what the last command was before power was lost. So, given that it seemed I was able to correctly capture and process the DCC signal, I was able to successfully expand the packet processing to setting a white LED for a forward speed instruction and a red LED for a reverse speed instruction. With that working, I did also try a third approach to the interrupt and packet handling, which was essentially a hybrid of the other two approaches. The interrupt service routine was detecting the packet preamble and the packet end bit, and storing the bits of the packet between them into a buffer, but doing it all with 8-bit numbers. It didn't work though, so that must have still been too much processing to be faster than the signal. I made a start on a fourth approach. The idea was to have packet processing work in parallel with the interrupt service routine, to make use of any spare processing time in between DCC values. But as I got further with it, it just started to look like a much more complex version of my second approach, so I decided to keep things simple and abandoned it. Having settled on an approach, I then extended the packet processing a bit further to handle long addresses, responding only to commands for address 221. I also implemented the error checking method described in the standard, though I think the standard is ambiguous. The standard says to do an exclusive OR over all of the bit positions for the address and instruction bytes. When there was only one address and one instruction byte, this was clear, but there doesn't seem to be a single definition of exclusive OR for more than 2 inputs. Some internet searches suggest 3 different definitions, one of which is that exclusive OR doesn't exist for anything other than 2 inputs. I decided to go with however C handles it. I just give all of the inputs to its exclusive OR operator, and that's passing the error check on DCC packets. Out of curiosity, I also tried Python's exclusive OR, and it gave the same results as C. That's everything I've done with the ATtiny85 so far. The Raspberry Pi Pico was a good place for me to start with this project, because I found programming them using MicroPython very straightforward, and I've already got everything set up on my computer to be able to do that. However, I found that the Pico with MicroPython wasn't able to keep up with the DCC signal, which I explained in the previous video. There were several key themes in comments that I got on that video, one of which was that the Raspberry Pi Pico has a feature called PIO, which is ideal for tracking fast input signals and producing something the MicroPython code could process separately. As a point of interest, I did, after a fair bit of faffing, manage to program the Pico using C rather than MicroPython, and did a rudimentary test of how quickly it could take a voltage measurement from an input pin. As expected, it was a lot faster, on average by about 60 times. If I were making below-board accessory decoders, or maybe using larger models, a Pico might be a really good way to go. But for my N-gauge models, even a very minimal development board like this RP2040 won't fit inside most of my locomotives. The RP2040 microprocessor itself is small, roughly 7mm square, but I don't fancy my chances of being able to solder anything to its tiny pins. The ATtiny85 on the other hand is a bit smaller overall and has fewer but much larger pins, so I feel like I actually stand a chance at putting something together with these. They've also been around for a long time, so there are plenty of tutorials around on how to program them, which is essential for me at this stage. The first real application I want to handle with a homemade DCC decoder is control of the lights on my Dapol Super Voyagers, which require 2 decoders each just for directional lights on DCC. The code I've got isn't far from being able to do that, it just needs expanding to handle an extended packet format command for enabling and disabling the lights. I think the big challenges for me will be getting a compact circuit board together using smaller surface mount components, so that's likely to be the next area I approach with this project. There have been plenty of times when I've started to doubt I'll be able to achieve my aims with this project. There's just so much I need to learn about the electronics, but so far perseverance has paid off and makes any progress very satisfying. That's all for now. Bye bye!